All right, we're going to wrap up Unit 6 today with topic 6.10, which is integrating with long division and completing the square. And when we're integrating with long division, just a couple notes here. Algebraic methods may be used to transform an integrand. We've already done that a little bit. And long division rewrites a rational, remember what rational means? Fraction. Fraction integrand is a sum of polynomials in a rational function with lower degree numerator. The best way to do this is to get into a problem. So let's look at this first problem. And what we're going to do here is we're going to use long division to clean this thing up first. So that means x plus 1 goes on the outside. All right. And on the inside, I have 5x squared plus x minus 1. Now, I will note on this problem, couldn't I also use synthetic division? How do I know? I can use synthetic division so long as what I'm dividing by just has an x. Like x minus 3. I could divide by x minus 3 or x plus 7, but I could not divide by 3x minus 4 using synthetic division. All right? So I don't care which one you use, but you do need to be aware that you can't use synthetic division all the time. All right? That is important. So let's do long division here. We ask, what do I multiply x by to get 5x squared? And that's 5x. So 5x times 5x, or 5x times x is 5x squared plus 5x. But remember, we subtract now. All right? So now we have to do some subtracting, and that means this thing is going to change into a minus and a minus. So these two terms always go away. That's what we want. And now we have a negative 4x minus 1. And I ask, what would I multiply this x by to get negative 4x? And that would be negative 4. So I have negative 4x minus 4. Since I'm subtracting, I change my signs. And I have a remainder of 3. So what do we do with the remainder? We put it over what we divided by. So now my integral is the integral of 5x minus 4 plus 3 over x plus 1 dx. We can split this into 3 integrals. We're allowed to do that with our rules of integrals. I can make this the integral of 5x dx minus the integral of 4 dx plus 3 times the integral of 1 over x plus 1 dx. And now it's fairly easy to clean this up. I'm going to have 5x squared over 2 here. I'm going to have minus 4x here. And I'm going to have plus 3 times the natural log of x plus 1 here. And I have plus c. So we were able to use division. We did it with long division. You technically could have used synthetic division on this problem, and that allows us to get this problem cleaned up pretty quickly. Let's take a look at this one. And this is an example of why I reviewed long division. You cannot use synthetic division on this one. Cannot use synthetic. So we put our x squared plus 1 outside. We put our numerator inside. and we start our division. So I need to multiply by 7x, which turns this into 7x cubed plus 7x. Where do I put that? I need to line it up over here, like that, and then subtract. All right, so these again are going to change into negatives, minus and minus. And so everything goes away when I do that. These go away, this goes away, but I still have to bring down this 11x squared. 11x squared, and then I have this plus 5. So then I ask, what do I multiply x squared by to get 11x squared? And that's 11. So I need a plus 11. So I multiply, and I have 11x squared plus 11. I'm going to change my signs. So this is going to be a minus and a minus. And I'm going to have a negative 6 here. Negative 6 is my remainder. It is over x squared plus 1. Which is why this is a good example. We look at what my integrand looks like now, and I have the integral of 7x plus 11 minus 6 over x squared plus 1 dx. And when we start thinking about antiderivatives, this one right here should stick out to us. That should stick out as one of our inverse trig functions. All right? And this one here is arctangent. So this one I'm going to have a minus 6 arctangent, or tangent to the negative 1 of x. The other pieces are pretty easy. This is 7x squared over 2. This is 11x. And then I have my plus c. All right, so that's an example of using long division. The other method that we can use is completing the square. And once again, we can use algebraic methods. And so we can use completing the square to kind of repackage this thing. All right, so let's repackage this thing. Let's use different wrapping paper on this problem by completing the square. So what we're going to do is we're going to take this x squared plus 6x plus 10 and we're going to complete the square with it. How do we do that? Well, we put this x squared plus 6x here. We stick this plus 10 over here out of the way. We did this in pre-calculus. And then we ask, what is half of the b term? It's 3. Then we square it. So I'm going to add 3 squared. Now, if I was doing this in an equation, I would just add 3 squared to both sides. But since I'm changing an expression, I don't just add 3 squared, I need to subtract 3 squared. That way I don't change the expression. All we're doing is we're changing the packaging of this problem. So look what we have now. This thing right here is the square of a binomial. That's why completing the square is so handy. This is x plus 3 quantity squared. All right. And over here I have negative 9 plus 10 So I have a plus 1. All right. And if you look at what we have now, I pull this 8 out in front, and I have the integral of 1 over x plus 3 quantity squared plus 1. And that may not seem very significant to you, but we're thinking inverse trig function again. Now we will have to do a u substitution. If I let u equal x plus 3, then du is just 1 dx. We don't even have to introduce anything. And I have 8 times the integral of 1 over u squared plus 1 du. And that's the one we just used, isn't it? Isn't that arctangent? This is arctangent. So this is going to be 8 times the arctangent of my u, which was x plus 3 plus c. Pretty easy. You just have to know what you're looking for. You have to be aware that these, when we're doing these rational expressions, you're going to have some of these inverse trig deals showing up. Let's look at one more. So, what we're going to do on this problem is we're going to complete the square with this thing. So let's bring it up here, and let's repackage it a little bit. We've got negative 4x squared plus 8x. All right. Now what we do in this case is we factor out a negative 4. We did this back in pre-calculus. We factor out a negative 4, and I'm left with x squared minus 2x. All right. Now, we complete the square with what's left. Half of the b term is going to be 1, so we square it, we add it, but we also subtract it because we don't want to change the expression any. We're just repackaging it using completing the square. All right. So what I have now is I have negative 4, and in parentheses I have this x minus 1 quantity squared, but I've also got this minus 1 here, like that. And if I distribute this negative 4 through, then I have negative 4 times x minus 1, the quantity squared, plus 4. Now that's one way you could do this. You could think of it that way. But let's just kind of, work with this a little bit and see what we get. So we have the integral now of 1 over the square root of negative 4 times x minus 1 quantity squared plus 4. So if we look at this thing in a little bit different package now, and this is where maybe a little bit of my guidance will help here. Let's make this the square root of 4 minus 4 times x minus 1 quantity squared. Let's make it look like that. And then let's factor that 4 out. So I have the square root of 4 times 1 minus x minus 1 quantity squared. And you're going to see why we're doing this in a second. Now we know that this square root of 4 can come out. It's 2. So now we can put a 1/2 out in front of 1 over the square root of 1 minus x minus 1 quantity squared. And this should look familiar to you. This is arc sine. All right? Obviously, I'd have to do a u substitution and make u equal x minus 1, but it's pretty easy because my du is just dx. All right? So what I have is 1/2 times the arc sine of x minus 1 plus c. And it's really more about manipulating these problems to get them into something that we know the antiderivative of. And completing the square, like we did up here, can help us get there. So you have to know when you're doing these problems, these rational problems, we're often going to be looking at an inverse trig situation. And we will stop there for today.